Okay, let's look at the Chinese remainder theorem and the Euler phi function in this section. So let me give you an overview. There's two versions of the Chinese remainder theorem I want to talk about. First is what I call an algebraic version, which is given in terms of a ring isomorphism, the ring of integers mod m, being isomorphic to a direct product of rings of integers. The second version is what I call the classical version of the Chinese remainder theorem. It's where its name comes from, given a bunch of different remainders. Then we'll look at the decomposition of the group of units mod m, so the group of units mod m being isomorphic to a direct product of subgroups of this type. We'll introduce the Euler phi function and show that it's a multiplicative function, and then finally derive a formula for the Euler phi function. So in order to understand the Chinese remainder theorem, you should spend a little time just reviewing the first isomorphism theorem from ring theory, if it's been a while since you've seen it. So those of you who need more time, you can read this page here, just reminding us what homomorphisms and isomorphisms are. And you can read the proof of the first isomorphism theorem given down at the bottom here in the appendix to our notes. So what is the algebraic version of the Chinese remainder theorem? So I'll let m1 through mk be pairwise relatively prime integers. So pairwise relatively prime means that no two of the mi's share a common prime factor. I'll let m be the product of these k integers, and then I claim we have a following ring isomorphism, that z mod m is isomorphic to z mod m1 cross z mod m2 cross ... all the way down to z mod mk. So isomorphism again means there's a one-to-one correspondence between these rings that preserves the multiplication and addition structure. Okay, to prove this, we'll just construct an isomorphism. So I'm going to define a mapping eta from z into z mod m1 cross z mod mk as follows. I'll say that eta of any integer x is what? Well, it has to be an element of the right-hand side, and the right-hand side is a k-tuple of objects. So this will be a k-tuple, where the first coordinate is the value of x mod m1. The second coordinate is the value of x mod m2. And the kth coordinate is the value of x mod mk. Well, then plainly this is a ring homomorphism. Right, if you want to look at eta of x plus y, that would mean you're putting an x plus y into each one of these coordinate positions. And what's the definition of addition in the Cartesian product? So in this coordinate, this just means x mod m1 plus y mod m1 all the way down the road to x mod mk plus y mod mk. But this just means take the tuple of x values and add it to the tuple of y values. Right, that's the definition of addition in a Cartesian product, just coordinate-wise addition. And of course this is eta of x, and this is eta of y. So eta of x plus eta of y. And similarly, eta of x times y is eta of x times eta of y. Okay, so we have a ring homomorphism. And now I want to look at the kernel of this homomorphism. I want to find all elements that get mapped to the 0 element. Okay, let's find the kernel of eta. So x is in the kernel. By definition, means that eta of x is the 0 element in this Cartesian product, which is just the vector all of whose coordinates are 0. Okay, but what is eta of x? Eta of x, by definition, is take the value x mod m1 down to the value of x mod mk, and we'll just set that equal to 0, 0, all the way down the road. Aha! That means that all the coordinates match up, so x mod mi has to be 0 mod mi for all values of I, going from 1 to k. And that means that x itself is congruent to 0 mod mi as I goes from 1 to k. And that means what? So we just keep unraveling definitions here. This means that mi is a divisor of x. As I goes from 1 to k. Okay, now, we haven't used a key hypothesis yet. What was the other hypothesis we had? That the m sub I are pairwise relatively prime integers. And so you have a homework problem that says if two integers are relatively prime and each is a divisor of x, then their product is a divisor of x. So this is in turn equivalent to saying that m1 times m2 times mk is a divisor of x, since the m sub I are pairwise relatively prime, which is equivalent to saying that m is a divisor of x, since that's the definition of m. Therefore, what's the kernel? Thus, the kernel of eta is exactly the set of multiples of m. So the principal ideal generated by m. So by first isomorphism theorem, we get z mod the kernel, so z mod m, is isomorphic to eta of z. So what is left is for us to show that this is really an onto mapping, that eta of z fills up the entire right-hand side. But that follows easily from a cardinality argument. So we've got that the cardinality of Zm is m, and this equals the cardinality of eta of z, because these two sets are isomorphic in one-to-one correspondence. So the cardinality of eta of z is also equal to m, but it's a subset. Eta of z is a subset of this right-hand side, z mod m1 cross z mod mk, and so what's the cardinality of the right-hand side? Since the cardinality of z mod m1 cross z mod mk is just m1 times m2 times mk, which equals m, this must in fact be all of the right-hand side. You've got m elements on the left, right here, and you've got m elements on the right-hand side, and so since this is a subset of the right-hand side, these two sets must be equal. We must have eta of z equals zm1 cross zmk, completing the isomorphism. Okay, now let's turn to the classical way of looking at the Chinese remainder theorem. So just what does this onto feature tell us? So let's again write down the onto feature. We have this mapping that takes x into this Cartesian product, where x is going to, so this is the end of the proof here, x mod m1, x mod mk, and we said this is an onto mapping. Well, if it's an onto mapping, that means if you hand me any object in this Cartesian product, so say you have me an a1 mod m1 and an ak mod mk, that there will exist some x that gets mapped to that object. All right, so that's the clue about the classical statement. So let's write it down. Suppose that m1 through mk again are pairwise relatively prime integers, and that a1 through ak are any integers. Then I claim there exists an integer n such that n is congruent to a sub I mod m sub I for all values of I from 1 to k. That is, and here's where the name of the theorem comes from, a sub I is the remainder in dividing m by m sub I. Moreover, the set of all solutions is just a single residue class mod the product of the given moduli. And again, the proof is just what I was outlining on the previous slide. So, by the previous theorem, there exists some integer x such that eta of x is this given tuple. So a1 mod m1, ak mod mk. That is, and remember, what is eta of x? That's just the value of x mod m1, comma, the value of x mod m2. So the value of x mod mi should equal the value of a sub I mod mi. That's just the definition of what does eta of x mean. And this statement is equivalent to saying that x is congruent to a sub I mod m sub I going from 1 to k. Okay, so x is playing the role of the value n that we were looking for in the theorem, and then the fact that this is an isomorphism tells us there is exactly one value of x mod m that satisfies this solution. So this moreover part, the second part of the theorem, follows from the isomorphism. Z mod m is isomorphic to Z mod m1 cross Z mod mk. In other words, if once you have specified these values a1 through ak, that gives you one object on the right hand side, and there would be a single object mod m that corresponds to that value. So a single residue class mod this product right here. Alright, let's do an example, because in practice, when you want to actually solve a Chinese remainder theorem problem, you're not going to ram it through some isomorphism theorem. So let's find all integers x such that x is congruent to 1 mod 6 and x is congruent to 2 mod 37. So note that these moduli are relatively prime. 6 and 37 share no common factors. And so what I'll do is I'll start with the largest modulus. That makes arithmetic easier, to start with the largest modulus and translate that into an equation. So x congruent to 2 mod 37 means that x should be of the form 2 plus 37t for some integer t. And then I just substitute this in to the first congruence. So then x congruent to 1 mod 6 would mean that 2 plus 37t is 1 mod 6. Subtracting 1, we get 37t. Well, 37 is what mod 6? 37 is 1 more than 36. So this gives us t is congruent to 1 minus 2, which is negative 1. Or in other words, that t is of the form negative 1 plus 6u, with u being an integer. And then I substitute that back in for x. So x is of the form 2 plus 37 times t, which is negative 1 plus 6u. And we get 2 minus 37, which is negative 35, plus 37 times 6u, where u is just some arbitrary integer. And so you can see plainly that we are getting a single answer, negative 35, mod this modulus, 37 times 6, which is the product of the two moduli we started with. So thus, x should be congruent to negative 35 mod 6 times 37. Okay, next let's look at the structure of the group of units mod m, gm. And we'll do this in two stages. So today we'll just prove the first theorem. If m is a positive integer with prime factorization p1 to the e1 times pk to the ek, then the group of units mod m is isomorphic to the direct product of the group of units mod p1 to the e1 times the group of units mod pk to the ek. And this isomorphism is multiplicative groups. All right, I claim this follows immediately from the algebraic version of the Chinese remainder theorem. So we have that Zm is isomorphic to Z mod P1 to the E1 cross Z mod Pk to the Ek by the Chinese remainder theorem, since, what's the hypothesis we needed in the Chinese remainder theorem? We needed the moduli to be pairwise relatively prime. And these are distinct prime factors here, since the Pi to the Ei are pairwise relatively prime. Okay, now this isomorphism is a ring isomorphism. So in particular, the isomorphism preserves the product structures in these two rings. Now sitting inside of Zm, you've got a group of units Gm. And sitting inside of this, there is another group, let's call it U. So thus, the group of units on the left-hand side is isomorphic to the group of units on the right-hand side, where capital U is the group of units in this Cartesian product ring. Z mod P1 to the E1 cross Z mod Pk to the Ek. So this is a result from ring theory. If two rings are isomorphic, then the group, the multiplicative group of units in the two rings are isomorphic as groups. Then I have to ask, well, what is the group of units on the right-hand side? Well, this is a Cartesian product. And if you want to get the group of units in a Cartesian product of rings, you have to have coordinates such that the first coordinate is a unit in the first ring, the second coordinate is a unit in the second ring, and the last coordinate is a unit in the last ring. So the group of units on the right-hand side is just the group of units mod P1 to the E1 cross the group of units mod Pk to the Ek. And so we are done. We get that the group of units mod M is isomorphic to this Cartesian product of the group of units. Now in proving this theorem, I've relied on two facts from ring theory, and I'll leave these as homework exercises. So we use the following fact. If two rings are isomorphic, R1 and R2, and U1 and U2 are the groups of units in the rings, then U1 is isomorphic to U2 as groups. And the whole idea is you've got this isomorphism, say eta, between these two rings, and then all you do is you take that mapping and you restrict it to the group U1. And I claim that this gives us the isomorphism between U1 and U2. So that's a homework problem. The second fact we need is that if you're looking at a Cartesian product of rings, then the group of units in the Cartesian product is just the Cartesian product of the group of units in the individual component rings. And again, I'll leave that as a homework problem for you to work out the details. Okay, now let's look at the multiplicative property of the Euler phi function. So what do I mean by calling it multiplicative? The Euler phi function is multiplicative. That is, if a and b are positive integers with a and b relatively prime, then phi of a times b is phi of a times phi of b. So it's not quite a multiplicative homomorphism, because you have to restrict a and b to have this condition right here. It's not true for all values of a and b. And to prove this, we just use the isomorphism we established. So by Chinese remainder theorem, we have that Z mod A times B is isomorphic to ZA cross ZB, since A and B are relatively prime. And then I just look at the groups of units. So this implies, we just repeat the argument of the previous theorem, that the group of units on the left-hand side, which is GAB, is isomorphic to the group of units mod A cross the group of units mod B as groups. And this implies they have the same cardinality. So the cardinality of the right-hand side is just the product of these two cardinalities. And so that implies that phi of AB equals phi of A times phi of B. As quick as that. All right, let p to the k be any prime power. And I want to determine phi of p to the k. So I just lay down all of the numbers from 1 to p to the k. And I want to cross off numbers that are not relatively prime to p to the k. So the first such value would just be p. And then you go to p plus 1. The next value would be 2p. Right? These have, whenever you have a factor of p, that's when you would not be relatively prime to p to the k. So these numbers I want to cross off my list. You'd have a 3p. Well, how many multiples of p are there until we hit p to the k, which I also want to cross off the list? Well, 1 out of every p numbers is a multiple of p. So there are p to the k minus 1 multiples of p in this list. And therefore, phi of p to the k would be all the remaining numbers. So we started with p to the k, and we've crossed off this value. Okay, so it's very easy to evaluate the Euler phi function at a prime power. And then to get the Euler phi function at any value, we just use the multiplicative property. So if m is a positive integer with prime factorization, product of pi to the ei's, then the Euler phi function is just the product of pi to the ei minus pi to the ei minus 1. And there's another way of expressing this where you factor out the m, and so you can think of the Euler phi function as being a certain fraction of the total number of integers going from 1 to m. So you'd have this product of these fractional quantities, 1 minus 1 over p sub I. And again, the proof is straightforward. By the multiplicative property of the Euler phi function, this is phi of the product like this. And so that would be phi of p1 to the e1 times phi of pk to the ek, or in other words, the product. I goes from 1 to k of phi of pi to the ei. And then we just evaluated that product on the previous slide. So that's pi to the ei minus pi to the ei minus 1. All right, and then to get this final form, all I do is I think of factoring out a pi to the ei like this. And that would leave me with a 1 minus 1 over pi. And then group together all of the first power terms, and that'll give me the m. And then I group together all of these pieces. Simple as that.